Hello students, welcome back to the chemistry class. In the previous class, we have studied about the basic concepts of electrochemical cells and also the use of Nernst equation for the calculation of electrode potentials. Today we will see how we can use Nernst equation for the calculation of cell potential. Now consider a zinc copper electrochemical cell. Zinc copper electrochemical cell. It can be represented as zinc oblique zinc ion, then salt bridge, then copper ion getting reduced to copper. Or we can write the overall reaction that zinc reacts with copper ion to give zinc ion plus copper. Now by using Nernst equation for electrode potential for oxidation half cell, that is anode, which is zinc here, we will write electrode potential for zinc ion will be equal to standard electrode potential for zinc ion minus 2.303 RT upon NF log 1 upon concentration of zinc ion. Let it be equation number 1. Same way for reduction half cell, that is cathode, which is copper here, we will write electrode potential for copper ion is equal to standard electrode potential for copper minus 2.303 RT upon NF log 1 upon concentration of copper ion. Let it be equation number 2. Now, cell potential is equal to standard electrode is equal to electrode potential of cathode, which is copper here, minus electrode potential of anode, which is zinc. So from the two equations we can take the value and write that cell potential will be equal to electrode potential of copper ion can be written as standard electrode potential of copper ion minus, from here we will take for zinc, standard electrode potential for zinc. From the second part we can take out 2.303 RT upon NF common, then in the bracket log 1 upon concentration of copper ion minus log 1 upon concentration of zinc ion. Now we all know that the difference in the electrode potential of cathode and anode is the cell potential. So this difference represents standard cell potential. So we write here that cell potential will be equal to standard cell potential minus 2.303 RT upon NF log m minus log n, that's equal to log m upon n. So we will apply it here and we will get log concentration of zinc ion upon concentration of copper ion. Or we can also write it as that cell potential is equal to standard cell potential minus 2.303 RT upon NF log concentration of ions at anode upon concentration of ions at cathode. So using this formula we can calculate cell potential for any cell at any concentration and temperature. We can also modify this equation for 298 Kelvin temperature and we can write it as at 298 Kelvin cell potential can be written as standard cell potential minus 0.059 upon n log concentration of ions at anode to the concentration at cathode. We can also write it as cell potential is equal to standard cell potential minus 0.059 upon n log Q, where Q is reaction quotient. Now let us see some calculations, some examples of numericals of calculation of cell potential using Nernst equation. Now here is the question. We have to calculate the EMF of a cell in which following reaction is taking place. Here nickel is getting oxidized to nickel ion. It means nickel is acting as anode. On the other hand, silver ion is getting reduced to silver. It means silver is acting as cathode. Here the values which are given are standard electrode potential of nickel and standard electrode potential of silver. So we can start here. So first thing which we need to calculate is standard cell potential. Standard cell potential can be calculated by taking difference of standard electrode potential of cathode, which is silver, minus standard electrode potential of anode, which is nickel. So we can write here it is equal to standard electrode potential of silver minus standard electrode potential of nickel. On putting the value, we will get 0.80 minus 0.25. That will be equal to 1.05 volt. This is the standard cell potential. Now, by using Nernst equation, cell potential is equal to standard cell potential minus 0.059 upon N, because the temperature is 298 Kelvin here. That's why we are using 0.059. Log concentration of anode ion, that's nickel ion, to the concentration of silver ion. Here there are two silver ions in the balanced chemical equation. So here concentration will be raised to power 2. Now we will substitute the values. We will get 1.05 minus 0.059 upon 2, because here 2 electrons are transferred. Nickel loses 2 electrons to change to nickel ion. Same way, 2 silver ions will gain 1 electron each. That's 2 electrons to change into 2 atoms of silver. Now, log concentration of nickel ion is given here 0.160. We can write it as 16 into 10 to the power minus 2, and concentration of silver 0.002. So we can write it here as 2 into 10 to the power minus 3 square. So we will get it here 1.05 minus 0.059 upon 2. On solving, we will get here log 2 square, that's 4, then 16 will be divided by 4. So we will get here log 4 into 10 to the power 4. Or we can write it as 1.05 minus 0.0295 into log 4 into 10 to the power 4 can be written as log 4 plus log 10 to the power 4. So log 4 is equal to 0.602 and log 10 to the power 4, that's equal to 4. So we will calculate it and we will get it here 0.0295 into 4.602. Further, on calculating, we will get it here 1.05 minus 0.136 on multiplying 4.602 by this. So our final answer will be 0.914 volt. So in this way we can calculate cell potential. Now let us discuss about determination of equilibrium constant from Nernst equation. As we all know that according to Nernst equation, cell potential is equal to standard cell potential minus 2.303 RT upon NF log Q, where Q is reaction quotient. At the point of equilibrium, the rate of forward and backward reaction becomes equal. So the cell potential also becomes 0. So we can write here that at equilibrium, cell potential is equal to 0 and the reaction quotient is equal to equilibrium constant. So now we can write as 0 is equal to standard cell potential minus 2.303 RT upon NF log Kc, or we can write that standard cell potential is equal to 2.303 RT upon NF log Kc. So this is the relation between standard cell potential and equilibrium constant. At 298 Kelvin temperature, we can write it as standard cell potential is equal to 0.059 upon N log Kc, or we can write that log Kc is equal to N into E naught cell upon 0.059. In this way we can determine equilibrium constant from the value of standard cell potential. Now let us derive a relation between Gibbs energy change and the standard cell potential. We all know that work done by an electrochemical cell is equal to the product of its EMF and the charge transferred. So we can write that work W is equal to charge into potential. If n moles of electrons are transferred here, then charge will be equal to N into F. So we can write that work is equal to NF, and in place of potential we can take standard cell potential. Now this work done by the cell is equal to decrease in its free energy. So we can write here that standard Gibbs free energy change will be equal to negative of NF E naught cell. So this is the relation between Gibbs energy change and the standard cell potential. If we use the value of standard cell potential from the equilibrium constant relation, we will get that E naught cell is equal to 2.303 RT upon NF log Kc. So on putting these values here, we will get that standard Gibbs energy change is equal to minus 2.303 RT log of Kc. So here is the relation between Gibbs energy change and the equilibrium constant. Now let us see a numerical of calculation of equilibrium constant and Gibbs energy change from the standard cell potential. Now here is our question. Determine the values of equilibrium constant and Gibbs energy change for this reaction. Here the standard cell potential is given 1.05 volt. So here first we can calculate the standard Gibbs energy change directly, because standard cell potential is given here using formula minus NF E naught cell. Even if standard cell potential is not given, then we can easily determine by taking the difference of standard electrode potential of cathode and anode. Now here when we will put the values, here N will be equal to 2 as 2 electrons are transferred. Faraday's constant we can take 96,500 and standard cell potential 1.05. So on multiplying we will get here minus 202,650 joule per mole, or we can write minus 202.65 kilojoule per mole. Now same way we can calculate the equilibrium constant. We know that log Kc is equal to N into E naught cell upon 0.059. So on putting the values we will get here 2 into 1.05 upon 0.059. On solving it we will get log Kc will be equal to 35.59. So Kc will be equal to anti-log of 35.59. So from the table we can find the value of anti-log here, and we will get here Kc will be equal to 3.89 into 10 to the power 35. So using this relation we can easily calculate standard Gibbs energy change and equilibrium constant. In our next class we will study about conductivity, conductance and resistance and some other properties of electrolytic solutions. Hope everything is clear about this topic. See you in our next class. Thank you.